We know how to use electronegativity values to determine what type of bond will form between two atoms. And we know that if the difference in electronegativity between two atoms is somewhere between 0.4 and 1.8, they will form a polar covalent bond in which the electrons are shared but unevenly. The atom with more of the electron density will be partially negative, and the atom with less of the electron density will be partially positive. That bond will have a bond dipole moment that is given by this equation, in which Q is the magnitude of the partial charges and R is the distance between the charges. We will represent that dipole moment with a vector, which is basically an arrow that shows both direction and magnitude. In other words, a longer arrow means a greater dipole. These vectors point in the direction of the electron excess. We can see here that a BF bond has a longer dipole vector than a CH bond because the BF bond is more polar. But we also want to be able to assess whether a whole molecule is polar or nonpolar, because if it is polar, it will have a net dipole moment. We can find the dipole moment of a molecule by adding up all the individual bond dipole moments. If there is a net dipole, the molecule is polar. If there is no net dipole, which can happen either if there are no polar bonds or if the vectors of the individual bond dipoles cancel each other out, the molecule is nonpolar. For diatomic molecules, the net dipole moment is just the individual bond dipole. If the bond is nonpolar, the dipole is zero. If the bond is polar, the dipole is determined by the bond dipole moment. But if we get into larger molecules with 3 or more atoms, we have to take into account the geometry of the molecule to see how the bond dipole moments will add up. Let's compare CO2 and water. These each have polar bonds, whether CO or OH. But CO2, being linear, when we add up its bond dipole moments, they cancel out because they are equal in magnitude and opposite in direction. So CO2 is a nonpolar molecule. Water has a bent molecular structure due to the lone pairs on the oxygen atom. So the individual bond dipole moments point slightly in the same direction. That means when we add them together, there will be a net dipole moment, and therefore water is a polar molecule. If we replace an oxygen atom on CO2 with a sulfur atom, it will become polar because the CS bond has a weaker dipole than the CO bond, so the net dipole will be slightly to the left. Things can cancel out in more than two directions. BF3 is nonpolar while NH3 is polar, due to the difference in geometry, trigonal planar versus trigonal pyramidal, meaning the NH bonds all point somewhat in one direction. This can work for 4 directions or more as well. Symmetry will be the key. Polar molecules tend to align themselves with an electric field, whereas nonpolar molecules do not. The polarity of a molecule also determines its melting and boiling point, its solubility, and so much about how it does chemistry, so we will need to be able to determine the polarity of a molecule.